Oh, wrong one here. All right, and we're gonna start this section on what derivatives tells us about the shape of the graph. Okay. Oh, I'm passing this back. Oh, do you mind? Yeah. Okay, now we did a little bit of talking about this in like earlier in the semester. I think it was like before test 2. And I did do a little bit of work on this, but we're going to expand on this topic. Now, this topic by itself is probably a pretty easy topic. Like anything that you do in this section is going to be relatively simple, just plugging things in and things like that. However, this section gets a little bit confusing because a lot of the times I think students mess up on trying to figure out what we're plugging numbers into which function, because there's multiple functions going around. There's a derivative, there's its first derivative, there's even its second derivative, and it's kind of confusing what you're plugging things into and what the answer should look like. Okay, now, 2 ways to go about this section. You can either memorize every type of question and every way that you can do things and what functions you're plugging things into. The easier way is to think about what you're actually doing before you start plugging things in. Okay, now I'll give you the tools to memorize it, but I honestly recommend that you actually think about what you're doing, because then you're not going to have to like memorize what to do in every single question that I'm going to ask you. Okay, so let's start with something easy. We have this increasing / decreasing test that the textbook gives. And what this is it's actually pretty easy. We talked about this before. Okay, when the derivative f prime of x is positive, what does that mean about the original function? Increasing, right? So the original function will be increasing. Okay, what about when the function or the derivative is negative? Decreasing, good. And then what happens when the derivative is 0? What's going on there? Constant, right? So it's either constant, which it actually is. So it's either like flat. Yeah, or it's like max or min, so it's like turning around. Let me pass this out real quick. Okay, so it is constant, but when I think of a constant function, I think of something flat. So I'm also going to say like, or turning around. Okay, so it either looks flat or it looks like a max or min. Okay, so what we can do is we can use this increasing decreasing test to figure out where, our function is either increasing or decreasing. Now, the sign of our derivative can only change at a critical number, which is where our derivative doesn't exist or where it's equal to 0. Okay, so whenever you're asked to find if a function is increasing or decreasing, you have to find like the critical values, right? So you have to find the critical values. Okay, and by the way, just a reminder, the critical values is where our derivative either equals 0 or doesn't exist. Okay, but the function also has to exist there, right? But f is defined. But there's one other thing that makes this sort of question a little bit harder to think about. A function can change from increasing to decreasing also where our original function doesn't exist, right? And if that's kind of confusing to you, let's pretend our function doesn't exist at some positive value, like it's a vertical asymptote, and my equation is going like up, right? If my function doesn't exist at this point, it could change from increasing to decreasing where it doesn't exist at that vertical asymptote, okay? So we're not just finding the critical values, we're also finding, we're also looking for places where the original function doesn't exist either, okay? So I'm going to give you the tools to memorize what to do for each question, but I do recommend you thinking about what the question is so you don't actually have to think about, okay, what do I do for this question? What do I do for the other one? It's easier to think about, okay, what makes sense in this situation so you don't have to memorize that much for the test, okay? So increasing, decreasing, critical values, places where the function doesn't exist. Now this one's a little bit easy because I gave you a polynomial. So let's just figure out the critical values for this, okay? So critical values of my original function. Okay. Critical values, we have to find the derivative, right? What's the derivative of my original function?
12x to the third minus 12x to the 12x squared minus 24x.
Perfect, right? Just using the power rule here. Okay, now critical values, we have to figure out where our derivative equals 0. So maybe I'll set this equal to 0. Okay. Now I have a cubic function, which is kind of hard to solve. Any ideas on how we can find what our zeros are, Michael?
12x.
Yeah, take out a 12x, right? Was that what you're going to say, Michael? Good. Okay, so when I take out a 12x, oh, sorry, I took out a 12, but not an x. 12x, I'm going to get, what is it? X squared minus x minus 2, right? Okay. All right. Maybe I can factor that x squared minus x minus 2. For those of you who need the adding and multiplying to, we're looking for two numbers that add to what number?
-1.
-1, right? And multiply to?
-2.
-2, good. And what two numbers do that?
-2 and 1.
Yeah. So it looks like my factors are 12x, x minus 2, and x plus 1. And that's how I get my factors here. All right. To find the critical values, you need to set each of the factors equal to 0. I'm lazy, and I think I can actually just figure out what my answers are here. We've got x equals 0, right, for 12x. We got x equals 2 for x minus 2, and we have x equals -1 for x plus 1. Okay. Are there any values where my derivative doesn't exist? No, right? So f prime of x dne, we don't need that. And then we need to think about where our original function doesn't exist, because that can also be a place where we go from increasing to decreasing. And that's not true either, because, well, our original function is a polynomial, right? So looking at where f doesn't exist, we don't need to search for that either. Okay, so we found all the places where we switch from potentially going from increasing to a decreasing place. Let's actually draw out a way that we can kind of systematically figure out if we're going from increasing to decreasing. Okay, so next step I'm going to do, I'm going to draw a number line. Okay, and I'm going to use my tool to make a really straight line. Okay, and I'll show you why I'm doing this in a minute. Okay, on this number line, I'm going to plot the three numbers that I'm interested in, the three candidates where we're switching or may switch from increasing to decreasing. I'm going to plot a 0, my -1, and my 2, and don't really worry about the spacing, okay? Underneath my number line, I'm going to kind of mark off sections so I can do something underneath each of the sections of my number line, okay? In each section, I'm going to test one value to see if a function is going to be negative or positive. What am I looking for? What am I going to plug my numbers into? Am I going to plug it into the original function, the derivative? If I plug it into the original function, what is that going to tell me about increasing or decreasing? Oh, okay. So you're saying, okay, if I plug in these values here, the derivative is going to be 0, and that's not going to tell us anything, right? Now, in each of these sections, I'm going to pick a point, like maybe x equals -2, because that's in the interval before -1. Now, if I plug that into the derivative, I won't get 0, right? So am I going to plug in -2 into the original function or the derivative? And why am I going to plug in the derivative?
Because the derivative tells you it's an increase or decrease, no constant.
Yeah, we want to know if the function is increasing or decreasing in that interval. So plugging it into the original function isn't going to tell us anything because it doesn't tell us anything. Plugging it into the derivative will tell us, okay, if it's positive, we're increasing. If it's negative, we're decreasing. Okay, so I'm going to just write this out. If you want to memorize how to do the question, go ahead. But I like knowing exactly what I'm doing. Okay, so we're plugging into the derivative. Okay, so there's multiple ways we can do this. I could plug -2 into this derivative, the 12x cubed minus 12x squared minus 24x, but that's going to be a lot of calculations, right? What I'm going to actually do is plug it into my factored form, okay? And I'll show you why it's a little bit easier when we do this, okay? So I know that my derivative is 12x, x minus 2, x plus 1, okay? I'm going to plug in -2. So we have 12 times -2. -2 minus 2 is -4. And -2 plus 1 is -1. Okay. Now I'm going to stop right here. What sign do you think the derivative is going to be? Positive or negative?
Negative,
Negative. And why is it going to be negative?
because it's because you have an odd number of negatives being multiplied together.
Yeah, there's 3 negatives. 3 is odd. If I multiply 3 negative things, I know that I'm going to get a negative number, okay? So I don't even care what number this ends up being. I just care if it's positive or if it's negative, okay? So the reason I picked the factored version of the derivative instead of the unfactored version is because, well, I know it's going to be a negative number. I don't care what the number is. I think it's easier working with the factored version instead of the non-factored version. Okay. Well, we know that, are we increasing or decreasing in the interval below -1? Decreasing, right? Negative derivative, decreasing. Okay. Let's do that with the other ones here. Let's find a number between -1 and 0. Yeah, -0.5 is good. Okay, same deal. I'm going to plug it into f prime of x, and more specifically, the factored version. We got 12 times -0.5. -0.5 minus 2 is -2.5. And -0.5 plus 1 is 0.5. Okay, so am I going to get a positive or negative number here? Positive, right? Because I have two negative numbers. They cancel each other out. Left with a positive number. This is definitely increasing. Okay. Let's keep going here. We got 0 and 0.2. What's a good number between those two numbers? 1, right? 1 is pretty easy to plug in. We got 12 times 1. 1 minus 2 is -1. 1 plus 1 is 2. So looks like I'm going to get a negative number here. So we got decreasing. Okay. And then I'm just going to pick a 3. That's a number bigger than 2. So I've got 12 times 3 times 3 minus 2 is 1. 3 plus 1 is 4. So this is increasing. Okay, I know I wrote really fast there, so I'll give you like 2 seconds to write that down. Yeah. Okay, so we found all the intervals where we're decreasing and increasing. Now, writing it in this chart does give us a lot of information, but I kind of want to write our answer in a more mathematical form, like maybe interval notation. Okay, so let's actually find all the intervals where we're increasing and decreasing. Okay, so let's do decreasing first. Okay, I know that between -infinity and -1, we are decreasing, right? I know that infinities get parentheses here. Okay, should -1 have a parentheses or a bracket?
Bracket.
Why do you say bracket? All right, why do you say parentheses?
Because it goes to a derivative that's zero, which is positive, no, neither positive nor negative.
Yeah, right. We're looking at where the derivative is negative. I know at -1, the derivative is 0, right? So if the derivative is 0, I'm not actually decreasing at -1, okay? So I'm going to put a parentheses here because at -1, the derivative is going to be 0, okay? I'm only interested where the derivative is negative, okay? Now we have another interval where we're decreasing between 0 and 2. And just like the other ones, parentheses, right? Okay, so those are all the intervals where we are decreasing. All right, let's do increasing. Pretty self-explanatory here, right? We just have -1 to 0 and 2 to infinity. Okay. All right, so I put the graph of the function up here. We found -1 as one of our critical values. We got 0 and 2. And looking at the graph, it looks like we actually did find the intervals of decreasing and increasing. Between -infinity and -1, it looks like we have a decreasing graph, right? Between -1 and 0, we have an increase. Between 0 and 2, we're decreasing. And between 2 and infinity, we're definitely increasing. So it looks like what we did was correct. Okay. If you have one of those fancy graphing calculators, I recommend checking to see if your answer makes sense at the end of this. Now, what you can't do is go in your calculator, find the intervals of increase and decrease, and not show your work. Okay, so calculators are good to check your work, but I definitely want you to show the steps when you do the question. Okay, so overall, found the critical values, found the places where the function doesn't exist, set up our chart, and plug into the derivative, okay? All right, if you flip the page over, I have a slightly harder derivative. I'm gonna give you a few moments to try this one. Same sort of deal. Definitely think about where the function doesn't exist, okay? And we'll come back in a tiny bit. All right, let me just do the derivative on the board. If you're done that, just keep working. But let's just do the derivative real quick, okay? The quotient rule says f over g prime is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, right? So the top is always f, the bottom is always g, okay? Doing this, we got g, which is 4x plus 4, times the derivative of the top, well, x squared becomes 2x, right? Minus the top times the derivative of the bottom, which is 4, all over the bottom squared. Okay, so that's what you'd start with the derivative here. Listen to the derivative. So you're gonna plug this. All right, I'm gonna go over this question just because I see a lot of answers written down. They all look really good, but I want to kind of make this a little bit more organized, especially with these questions. Staying organized is really important. So let me just go over how we would do this. I already found the derivative, but with these questions, it's kind of easier to factor or expand everything out. So things are a little bit nicer to work with. So the next thing I'm going to do is just take the 2x and multiply it over to both of these values here. So I'm going to get 8x squared plus 8x minus 4x squared over 4x plus 4 squared. Okay, now I saw a lot of people factoring out the denominator. I wouldn't do that just because it's a little bit easier to find where the derivative doesn't exist if we kind of leave it alone. So let's not do that yet, okay? Once we subtract, we should get 4x squared plus 8x over 4x plus 4 squared. Okay. Once I'm here, I'm going to do something. I'm going to do one more step here that might look a little weird, but I'm going to factor out the numerator. Okay. What can I factor out of the numerator? 4x, right? So that becomes x plus 2. So 4x times x plus 2 over 4x plus 4 squared. All right, so everything's all factored out on f prime. So we have the derivative. Next, what we have to do is figure out our critical values, right? So let's find our critical values. That's what comes next. Well, we have to find out where our derivative equals 0. Okay, and what's the easiest way to figure out where the derivative is 0? Yeah, or we could set the numerator equal to 0, right? So set the numerator equals 0. Our numerator is 4x times x plus 2. So the 4x gives us that x equals 0. The x plus 2 gives us that x equals negative 2. Okay, so we have two places where the derivative is equal to 0. Okay, we also have to find where the derivative doesn't exist. And what's the easiest way to figure that out? Set the denominator equals 0, good, the bottom. So denominator, oh my gosh, denom equals 0. So I'm going to set 4x plus 4 squared equal to 0. Okay. When we have a squared, how do we undo that? Square root, good. So I'm just going to take the square root of both sides. Now I'm not going to bother with the plus or minus because I'm taking the square root of 0. Doesn't matter there. So I'm left with 4x plus 4 equals 0. Okay, solving for 0, subtract 4 on both sides, get 4x equals negative 4. So x equals negative 1. Now remember, critical values is where the function exists and where we have either the derivative equaling 0 or the derivative does not exist. So is x equals negative 1, is that a critical value? No, and why not?
The original function doesn't exist.
Yeah, so this is not a critical value. Okay, so if I asked you to find the critical values, you wouldn't include negative 1 here, because if I plug negative 1 into the function, it wouldn't work, okay? But for this question, it actually is important to test things around negative 1. Okay, and the reason for this is because the function has a discontinuity here, okay? Now, I kind of drew this out last time, but I'm going to draw it again, okay? If my function has a discontinuity, for example, rational functions, we would have a vertical asymptote, okay? My function could be like increasing towards the vertical asymptote and then decreasing on the other side of the vertical asymptote, okay? So because of this, it's also important to test to see if, at that point, the discontinuity changes from increasing to decreasing, okay? So it's also important to test this. So not a critical value, but we will still test it. Okay. All right, so we found where the function equals 0, where the function doesn't exist. The places where our function doesn't exist, so f of x doesn't exist at x equals negative 1. There's no other places where the function doesn't exist, so we don't have to figure out any more numbers. Okay, we have all the candidates for our places where we switch signs. So what we're going to do here is draw our number line. Okay, I'm going to change colors here. Let's do purple. Okay. So we got 3 places in our number line. We have -2, we've got -1, and we've got 0. All right, let's make our sections here. Okay, under -2, let's say from -2 up to -infinity, what x value did you plug in? -3, right? And are we plugging this into the original function or the derivative? The derivative, right? We want to see if we're increasing or decreasing. So we're definitely plugging into the derivative. Okay, now there's multiple different versions of the derivative that we can plug into. We could plug into this thing, which would be a lot of calculations. We can plug into this thing, which would be kind of hard. But what I'm going to do is I'm going to plug into this thing because it's the factored version of my derivative. Okay, so because this is kind of factored, it might be easy to figure out what the signs of each multiple is. So I'm going to plug this into 4x times x plus 2 over 4x plus 4 squared. Okay, so plugging -3, we have 4 times -3. -3 plus 2 is -1. Anything squared is going to be something positive, but I guess I'll write it down. 4 times -3 plus 4 is, I think, -8 squared. Okay, so it looks like we have a 4 times a negative times another negative over something positive because we have something squared. Okay, is this value going to be negative or positive? Positive, right? Looks like the -3 and the -1 cancel each other out. So this is going to be something positive. Okay. Next, let's plug in x equals maybe -1.5, right? That's a number between -1 and -2. We've got 4 times -1.5. -1.5 plus 2 is 0.5 over something squared, so something positive. Okay, is this going to be negative or positive? What value am I going to get here? Negative, right? Okay, now we need a value between -1 and 0, so maybe -0.5. This gives me 4 times -0.5 times, -0.5 plus 2 is 1.5. Good, thanks. Over something positive. Is this going to be negative or positive? Negative. And then finally, I'm going to plug in 1 because 1 is pretty easy to plug in. 4 times 1, 1 plus 2 is 3 over something positive. This is definitely going to be positive. Okay. Now let's talk about our intervals of increasing and decreasing. Okay, so this is a little bit hard to think about, but I think we can get it. Okay, let's do our intervals of increasing first. Okay, we're definitely increasing between -∞ and -2, right? That's where our derivative was positive. Am I going to have a bracket or a parentheses on -2? Bracket or parentheses? Here bracket, here parentheses. It's actually always a parentheses, right? Because at -2, our derivative is 0, right? We're only interested in where the derivative is negative, where the derivative is positive. So for these questions, we're actually always using parentheses, okay? We also have a positive between 0 and positive infinity. Let's talk about the intervals of decrease, okay? Now I have two options, right? I got -2 to -1 and -1 to 0. And I also have -2 to 0. Any ideas on which one of those it should be?
0.
Okay, so I have -2 to 0. Okay. I guess the big question is are we decreasing at x equals -1?
Well, it's just a whole, technically.
Yeah, right. Our function doesn't exist at -1. Okay, so can we be decreasing where the function doesn't exist? No, right? So since we have a hole here, the function doesn't exist, so we're not decreasing. Okay, so where are we actually decreasing?
-2 to -1 to -1 to 0.
Good, -2 to -1 and -1 to 0. Okay, so I know it's kind of confusing. This is why we plug in our discontinuities in our little chart, okay? Even if -1 is not a critical value, it's still important to think about when we're dealing with intervals of decreasing and intervals of increasing, because we're not decreasing when the function doesn't exist, okay? So this is my final answer here. Okay. Any questions on examples 1 or 2? All right, then I think what we have is, we have a quiz review to go over, right? So we have quiz 7 coming up tomorrow. I have a worksheet for you to work on. Just like last time, I will post the answers to this on my classes later today. But if you need to go somewhere